Welcome to a new video. In this video we will discuss the Z-transform. We will discuss the elementary functions. So we will give the Z-transform for these functions. We will discuss some parameters and properties. And of course we'll work out the example step by step and show you that using the Z-transform table. And we will also verify our calculations using the MATLAB command window. Alright, let's see first our introduction. The Z-transform, we have the following mathematical tool which is useful for analysis and design of discrete time or sample time control systems. This is the Z-transform. Like the Laplace transform that is used for continuous time systems, Z-transform is very useful in discrete time systems. For linear time invariant difference equations, not differential equations, it is converted into the Z-domain. So if you have a linear time invariant difference equation, that will be converted in the Z-domain. Okay, the solution of that equation becomes then an algebraic equation in nature. So instead of going with very complicated expressions, we just add and subtract and do some multiplication and division, like in Laplace domain, where you go from a very complicated differential equation in time to very simple additions, multiplications, etc. And the transformation from time domain into the Z-domain, that is the transformation we are talking about. Now, the discrete time signals, they are used in systems which include sampling operation of continuous time signals. And sample signals is then given by this expression, which is then x of k t, capital letter T, where the t is a sampling period given in a second, and the k is here the order. So we have some sample, let's say 0 sample, the first sample, the second sample, etc. So k is an integer. The Z-transform applies to continuous time signals. So let's say x of t for sampled signals. So x of k, capital letter T, and also for number sequences. Now for x of t or x of kt, the definition goes like so. So you go from the small letters to capital letters and you change the argument to z. And this is the script z for the Z-transform. That will then change. You can also use this in a summation, which is given by k is equal to 0 up to infinity by this expression. You see here the multiplication by z to the power minus k, which is also the Z-transform of this function. So this goes in, will be multiplied and processed using this summation. You can also look at the number sequence in a similar way and then use the summation, and you have here also the Z-transform. Now these two expressions are for one-sided Z-transform. You can also have double-sided or two-sided Z-transform when you go from k is equal to minus infinity to infinity, which is most of the time encountered in digital signal processing. In this case we only look at the positive values of k. Okay, now let's start with the elementary functions one by one. The first one is about the unit step function, which is a very important function. We encounter this a lot in engineering and science. Now the definition of the unit step function is given by this expression. You see here the x of t is equal to that unit step function, which is given by u of t, and which is 1 for time larger or equal to 0, and is 0 before that. So it stays that value, kept that value forever. Of course, you can make here 6 times the ut, so it will be then 6, so it is just amplitude in this case 1. So how do we determine the Z-transform of this very important function? So again, the definition, capital letter Z, which is then by this script expression. We need to go now to the part where it is valid, so not the part for the 0. And then we can use our summation now. Since this is always 1, because this is our unit step function, we will multiply that by z to the power minus k, and of course you can drop that 1, so that will be then only z to the power minus k. So we can now fill in this k one by one. First is 0, so z to the power 0, and then 1, z to the power minus 1, and then 2, z to the power minus 2, etc. And you have this expression. Now you can then have this in the simplified version, that this goes on, of course, to infinity. So we can express this series by a fraction which is actually shown here. So you can have, instead of this, which is discussed in great detail in calculus for infinite series, you have 1 over 1 minus z to the power minus 1, which is actually this one. You can also convert that to expression where you don't have this negative exponent, so you multiply the numerator and denominator by z, so you have z over z minus 1. This is the first z-transform of a unit step function. The next one is a unit ramp function. Unit ramp function is a linearly increasing function. In this case, again, valid for positive values of t, and for smaller values of t for 0, so negative, this will be 0. You can also express that in sampled version of the signal by k, capital letter T, for k is equal to 0, 1, 2, etc. for integer values. Again, using the definition, and put this kt instead of t here in this summation for the z-transform. Now what you get now is the following. Now since this t is just a sampling period, it doesn't have an effect on the k, so it's not influenced by k, so you can just put it outside the summation expression. Now we have only here k times 0 to the power minus k. So we can again move on one by one for the k's. And you can say 0 times 0 to the power minus 0, or just 0, and then 1 times 0 to the power minus 1, 2 times 0 to the power minus 2, etc. And we have here the t outside this large parentheses. Now what do we have then? Now this is 0, this is 0 to the power minus 1, 2 times 0 to the power minus 2. So this looks similar to that one. There's only not 1 here, and there's of course a different coefficient for each term here. And of course there's t here, but it's just a multiplication factor. So how do we again move from this expression to a fraction? Again, using the formulas from calculus, we can move on from here to there, which is 0 to the power minus 1 over 1 minus 0 to the power minus 1 quantity squared times t, of course. Again, if you don't want, and I also don't want that, negative exponents for your z, you can multiply the numerator and denominator. Now in this case we need to multiply that by z squared in order to go also in this squared term. So we get t times z, because z squared times z to the power minus 1 will be z to the power 1. So it's then t times z over z minus 1. So that's actually the, and then quantity squared. That is unit ramp function. Now very important function also, the polynomial function, which is given by this, in this case as a sequence, so x of k, a to the power k in this case is a is a constant, so, and also positive, so let's say 5 to the power k, and it runs for 0, 1, 2, etc. And for smaller than 0 for k, this function is 0. Again, the definition, now in this case a sequence for our z-transform. Now you can see that this a to the power k comes in here in front of the z to the power minus k, like in the previous two functions. Again, looking for k is 0, k is 1, k is 2, etc. One by one, this will be 1, this will be a to the power z, a times z to the power minus 1, a squared times z to the power minus 2, etc, etc. So this is actually going this fashion. And again, you can put this, because this is really similar to the first expression, and then you can put it in this form. And then you have, again, the multiplication by the numerator and denominator by z. You have the z over z minus a, as our z-transform of this a to the power k. And this is a very important transformation. Okay, let's now look at the next one, which is our exponential function. Also encountered very often in science and engineering. So we have in this case e to the power minus at. You see this is a decaying signal in time. So it will then approach 0. So we'll have a bounded or stable pole, as to speak. And for t is larger or equal to 0, we have this expression. For smaller than 0 for t, this function is 0. Again, we can do that in a sampled version, so k of k times t, and then we have then the replacement of t by k capital letter T, that's shown here, and this is again only valid for 0, 1, 2, etc. Again, we apply the definition of the z-transform, put this function here, so e to the power minus a kt. In this case, a is a constant, k is a running parameter here, and t is our sampling period. Now we need to again look at some values for k here, so 0, 1, 2, 3. So I actually put these values here. Now this will be a 1, this will be as shown here, this will be as shown here, this will be as shown here, etc. So again, we can put this like in the previous case in a fraction, like so, and again I can multiply the numerator and denominator by z, and I have this z over z minus e to the power minus a t, capital letter T in this case. So you see here is the following. If this is e to the power minus, let's say 70, so 7 smaller t, then we have z over the z transform of that time function is then z over z minus e to the power minus 7 capital letter T. Okay. Next one is about the sinusoidal function, so the cosines and sines. So let's start with the cosine. In this case, we start with the cosine of omega t. We have an amplitude 1, and the omega here is our radian frequency. There is no phase shift. And again, this function is only valid for positive time, so for 0 and larger, and for smaller than 0 of time, this function is 0. Again, we can right away start with the z-transform expression, but let's also look at it in more detail, maybe also to help us to work this out easily. We can use Euler's identity for the e to the power j omega, which is our exponential function. It can be then put in these two forms, so we have the real and the imaginary part. You can also put this minus again, but now the only argument is changing. This plus will be this minus. And how do we now convert these two equations for the cosine? So what I want is, I want to express this cosine in terms of this e to the power j omega, so in terms of these exponentials. So how to do that? Now you can add these two equations together. So then I will lose this sign. So I have then plus j sine omega t and a minus j sine omega t, so that I will lose that. I have on the right side 2 times the cosine omega t, and I have these two added together. So in order to have only one cosine omega t, I need to also divide the summation here, which is then shown here. So instead of going right away with the cosine omega t, we can better make the z transformation of this expression. Why? Because we know something about that e to the power some exponential function. So let's make that also useful here. So in order to find the z transform of this cosine function, we can also find the z transform of this function. Now let's put this half 1 over 2 out of this z transform expression. Now look at this and look at that. That is actually very similar to that one. So we can say again the note we have found in the previous exponential function that e to the power minus small letter a, small letter t was z over z minus e to the power minus at. It's capital letter T, of course, here. But remember, this is a minus, so this will be also minus. So what we have here is a plus. So we need to be careful. So we need to say z over z minus e to the power plus whatever that is, of course. And then j omega capital letter T. So we just take it over. So we only change actually the small letter t in the capital letter T, and the a is in this case j omega. In a similar case for the second term, that is as this one, the only change is the minus sign. Now we need to put these two fractions in one fraction because that's not really readable here. So again we have this half, but I can make these two fractions one fraction by making the denominators exact same by multiplying this by z minus e to the power minus j omega and this z by this expression. It's actually shown here in detail. So we have here, as shown, the same denominator, so we can add them up. So I do it here. So we have this and we have that. So we have here z squared. We have another z squared here. So if I multiply the parentheses out here, that means z squared plus z squared will be then 2z squared. I have here z times minus e to the power minus j omega capital letter T and plus and minus again. So minus z e to the power j omega capital letter T. So there is a z outside the parentheses and there are two arguments with positive and negative, of course, also minus in front of that z. That's all shown here. Now the denominator is again z squared and z times this one, and then minus j omega t capital letter T times z, and then this term, so minus j a e to the power j omega capital letter T times this will be the minus times minus, which was plus, but you see here e to the power j omega capital letter T times its inverse and the exponent will be just 1. So like e to the power j5 times e to the power minus j5 is also 1. Of course this is minus and this is minus, so they also cancel each other out. And this part here, the second term, is because of this multiplication here and this multiplication there. So we actually have this. So this is our z-transform here for this function. Of course it can be still be simplified and more readable. So what do you see? I can see that this 2 here and this 2, so they can cancel each other out. So there's a half here, so I can put it in. I can put also this half in here, so I do that. And now I have this expression. You can also say, in addition to the following, we already have some expressions for our exponentials. And this one here, a half times e to the power j omega t plus e to the power minus j omega t capital letter T. This one is actually cosine of omega capital letter T in this case, because we need to recognize this. So we can also, instead of this, put here cosine omega capital letter T. And a similar case is also here, but this is 2 times larger than what is expressed here. So you can also say 2 times this cosine is the summation here, which is shown here, and it's also shown here. So, okay, that's for the cosine. Let's do the exact same for the sine. Again, we can use this Euler's identity. Now we need to have the sine here. So expression for the sine, that means we need to subtract it. So you need to subtract the first equation minus the second equation. And then you have done this minus that. And then you have done 2 times j sine omega t. And then you need to also divide by the j2. That's actually shown here. So you see the minus sign here because of this minus sign here. Okay, now we have our sine expression. As said before, for the cosine, we can also proceed with this one instead of going for the sine omega t directly. So again, the z-transform for this one, instead of that, we go right away to the exponentials. We put out the 1 over j2 because that doesn't have anything to do with the z-transform. So we have this one. So again, we use the note from our exponential function. Again, we put everything here. You see, this is then exactly the same actually as we had before for the cosine, only this is a minus sign because there's a minus sign here. Nothing has changed. And we have here, instead of 1 over 2, 1 over j2. Now we need to again put these two fractions together, so I go a little bit faster because this is already discussed in detail. Now we need to put these two fractions now together, so minus sign here. So let's do that. Still 1 over j2 in front. Now we have here z squared, but we have now here minus z squared, so that's gone. So it's actually easier than before. And you have also here minus z times this one, and then plus z times this one. So that will be then like so. And we have here again this multiplication, which is actually again here. So how can we again make this more readable and easy? Okay, again I use this 1 over j2 here in the numerator, and I have this one, so I can recognize here this one is my sine here. So I can say, instead of this, I can say it is z times the sine omega capital letter T. But how about this? Now this is again the same thing, because we said before that the half of this one, so the summation of this one over 2 will be the cosine of omega t, so this is also the same. So the denominator is the same as for the previous z-transform of the cosine omega t. Now we have also the z-transformation of our sine of omega t. Okay, let's move on and now also discuss an example which is very useful if you want to go from a Laplace domain to the z domain. Now that goes indirectly. You can also do it directly, but indirectly is more easy to follow. Let's say we have an expression for our x, which is in the Laplace domain, which is now here a second order system. So 10 over s times s plus 2. And I want to have the x of z, which is our z-transform. How do we start? We start first with the partial fraction expansion of this one. So that means we need to expand this in two fractions, easy fractions, which is then some a, we don't know yet, over s, which is this, plus b over s plus 2, which is this. Now we need to find the a and b. Now we can again make these two fractions one fraction by again making the denominators equal to each other, like so. So a times s plus 2 times here s, and then we have also the same denominator as the left side. That's all the whole purpose. Now we can say 10 is equal to a times s plus 2 plus bs. Now how do we determine now the a and b? Now there are different methods. The method I really like is just select the convenient value such that only one unknown is left. So in this case, if I select 0, I only have here 10 is equal to 2 times a, which is actually shown here. So in detail, so a is then 5. So I think this is pretty fast and also simple. And for s is equal to minus 2, I lose this one, so I have only b. That means then 10 is equal to here, like so. And then I have now minus 2b, because this is a minus 2. And then b will be then minus 5. So I have now also the a and the b. Then we can write this expression originally given here as one fraction in two fractions. You might say, why do you want that? Now, if I look at my table, I can recognize this easily, and not always this. This is also maybe a, let's say, a row or element here in your Laplace table. But if you don't have that, for example, if you have a third or a fourth order, you still need to do the partial fraction expansion. So this is in general always useful. Now we need to go to the inverse Laplace transform. For inverse Laplace transform of this one, which is given here by the script L to the power minus 1 means inverse Laplace transform. We go to the time domain. So we make the conversion from the S domain to the time domain. And now we have this. Now 5 over S minus 5 over S plus 2. That's actually what we have. So how do we convert that? Now from the table we know this will be just a constant, so just a 5 here in the numerator, and this will be then minus here and a 5 and an e to the power, the negative of this one in the exponent times t. So you see everything here is in the time domain. We also have here 5, so let's also put it out, and then 1 minus e to the power minus 2t times 5. Now we can use a z-transform. So we apply here the z-transform. So we use the definition. Here's the z-transform. So we can say, let's put the 5 also out because that doesn't have any effect. So we need to find the z-transform of 1 and also the z-transform of e to the power minus 2t and then subtract it from each other. Now we know what the 1 is because that is the unit step function, which is always 1. So we can say we already know that is z over z minus 1. And this one from the previous discussion, the exponential, was actually like so. Now we have two fractions and we need to, so this is actually going from the table. So this is important. And now we can take these two fractions together in one fraction, again making these two fractions the same. So multiply this by this one and this by this one. Of course also the numerators. So you see that whole process. And now we can come up to this one 5 times, and then we have here this minus the z times z minus 1. And you have here the denominator we have in common. Okay, now we can again work out the parentheses, z squared here minus z squared, etc. So that is not really that difficult, I think, to follow. And we have here our z-transform from this Laplace expression. Okay. Now, let's also discuss the Z-transform table, because we have here the Laplace expressions. So we have here 8 entries. We have here time functions. We have here the x, kt, so as the sampled version, or also the sequence version. And we have also here the Z-transform of that one. So you see here the unit step function in time 1 over s, and it will be then z over z minus 1. And you can also have a ramp, which is then kt in the sampled version, and it will be then here as the tz over z minus 1 quantity squared. You have more, and if you need that, you can look at this table, so you don't have to start all from scratch. But sometimes you need to make that partial fraction expansion in order to get the right value. Okay, let's also discuss the second part of the Z-transform table. In fact, you can have more entries in your Z-transform table, so this is not a finalized form, but I have put here the most encountered equations in science and engineering. You will see here, for example, the polynomial again, the shifted version, and also multiplied by this shift. Okay, now let's see our first example. We would like to determine the Z-transform of this function, which is this decaying function of e to the power minus 4t times the cosine of 10t. So how do we work this out? Okay, let's see our calculation now. From the Z-transform table, we can see that's actually the part I took from the Z-transform. We can look at the n3 14 here. This is actually shown here. And you see now, recognize this a is, small letter a is 4, and omega is 10. So we can just look at this one. So that means here, going from the time domain to the z domain is like so from the table. So I just copied that. And now I need to move that to the z domain. Now recognize here, this will be then z squared minus z e to the power minus 4 capital T. I also have here 10 for the cosine of 10t. And then also etc. for the other ones. So because you need to just look at the a, small letter a, and omega. It's really that straightforward. And this is 2 times a, so you need to have a minus 8 here. Okay. And then what? Now you can still move on with this one and then make it a little bit easier to read. So there's a z squared here, there's a z here, so that means we can take the z out. So that's actually what happens here. You can also, if you say I don't like those exponentials with negative exponents, so we can also say I want to multiply the numerator and denominator by e to the power plus 8t, the capital letter T. This will be then 1. This will be then e to the power plus 4t. This will be, of course, e to the power 8t, because there is nothing here, so it's just 1. And now I have here in the parentheses, because I leave the z out, here e to the power 8t, and here e to the power plus 4t. I think also this is more readable because of this negative exponentials, so this is what we also can write down. Let's see also what we have in MATLAB. So in MATLAB, we have this script, so sims_t, that is actually, you define a symbolic variable. I call it in this case t, but you can also call it k, n, whatever you want to call it. So we have here now the x is then equal to. Now let's verify this result in MATLAB. Now this is the script in MATLAB. You define here using this sims_t, symbolic variable t. You can also choose another letter here. You can also say I want to use n. It doesn't matter. Now this is your function as we have it here. Now this is the function, you see that also. Now we here define the function as set, and we have also here using the z-trans and then small letter x is equal to capital letter X, that is our z-transform. And that is now the result. Now you can say, is this readable? Now let's see that. What we see here is not really that readable, and we also don't see the t, so I want to also point it out in detail. By default, the sampling period here is set to 1 second, so t is 1. Then the z-transform will be like so. So in our case, I want to compare this with that one, because this is given not in math print, just one row. I would like to see that this is indeed correct. So what do you see? Now, we have this. Now we have also z times, and z here is actually also multiplied by e to the power 4, because it's e to the power 4, and then times cosine 10 minus z e to the power 4, and then parentheses. So this last parenthesis here and this first parenthesis here is actually the numerator. Of course, there's a minus sign here, so that's actually why this is reversed. And there is also this e to the power 4 here, which is taking also outside this parentheses. So in order to write it down more clearly, maybe that's also better. So I also do that. You see that? So I have done that. So the denominator is exactly the same. So here's your e to the power 8 z squared minus 2 cosine 10 e to the power 4. So it's all here times z plus 1. And now if I want really the exact expression as MATLAB produced, I can put just a minus sign here and then flip this argument here, and I have exact the same expression as MATLAB has given. Okay, let's see another. So this is correct. Let's see another example. We have now here a multiplication of t times e to the power minus 60. How does it work in this case? Now if x has a z-transform, if that is the case, and then the z-transform of that function, so there is a new x, so something, and that function I multiply also by e to the power minus 80, that can be then given by this z-transform looking like so. So the argument z has changed from z to z e to the power plus at. What happens here? So let's see what this means. And this is, by the way, called the complex translation theorem, which is very useful in order to calculate the z-transform much faster and easier. We can also prove that. You say, let's see that in detail. So the z-transform of function is also given by this. So in this case we have a function, and now x in this case is, let's say, this t. So not this one, so I make that just a t, simple t. So what is that simple t? Now t was the ramp function. We can say x t kt, and we can also write it like so, because this x kt is our t, and this one here is our inverse, I mean the z-transform function, z-transform of this expression. So the exponential is there with the z in the parentheses to the power minus k, because this term, the third term here and the first term, will come together and produce this one. That's correct. So you see here, instead of z, you create a new parameter to do the Z transformation. Still the same function we actually do. Now we have this. This is indeed, as said before, the Z transformation for this multiplication. Now from the Z-transform table we can see the following. For t you have actually this tz over z minus 1 quantity squared. So what do we do now? Now if I now take the Z-transform of that t indeed, I can just copy that. That's simple. But how do I do that for this one? So let's designate as x of z. Now using the complex translation theorem, I can say in this case, instead of this one, I can also calculate that one. And I only need to replace the z by z times e to the power 6 capital letter T. That's the only thing. That means I take this one and replace the z by z times e to the power plus 6 capital letter T. So remember, it's not minus. So what do we have? It's here. So you just pick this z, replace that. Pick this z, replace that. That's it. It's really that simple. Let's see that in MATLAB, if that is really correct. So this is the script again. We define here a symbolic parameter. We make the function as we have it, and we determine the Z-transform, and this is the result. You see here, z times e to the power 6. So in parentheses, that's in the numerator, divided by z times e to the power 6, again, minus 1 quantity squared. Again, there is no t involved here, so the period, the sampling period, is assumed to be 1. So that is actually shown here, and this is also what we have. So we can say this is indeed verified. Let's see a little bit more complicated. So instead of t, we make it t squared. And I can use this complex translation theorem. Now we need to look at this, entry 5, the same table. Now we can use this. Now we can go a little bit faster, because we know that this t squared, the Z-transform of that t squared in time is this one, looking just to the table. And now we need to make that replacement of z by z to the power e at. So that's actually all what it is. In this case, we have a 6 capital T times z instead of z. So let's see what happens now. T squared, and then this is then z will be then this one, this z will be this one, and this z will be that one. Let's check that. Let's check if this is really correct, the MATLAB. As again, we define a function or a scalar variable. This is the function. This is how we determine the Z-transform, and this is the result. What you see? Now, we see actually here a parenthesis times something. Again, there is no time, or I mean the sampling time involved, so because that's t is 1 always by default. So you see here z times e to the power 6, which is what we have here. Here I mean, plus 1, this parenthesis, so this parenthesis, this one, times z to the power e to the power z times e to the power 6, which is this. So because if that t is gone, because that's 1 squared, and this is 1 here, so 6, 6, and 6 here, so we have this. So this is again verified, and also the denominator is correct, because that's the whole thing to the power 3. So we can see that this is indeed correct. Let's see another example. And this example is about this sequence, which is given by k squared. So let's see how we do that using the definition of the Z-transform. Now, the definition of Z-transform is shown here. We can again put that in the summation, and then k squared z to the power minus k. So let's work out some terms. So I do that here for several terms here, and we do here, for example, z, so that means 0 squared times z to the power 0, then 1 squared times z to the power minus 1, etc. So this will result in this, because that's gone, and then we have this. So we see here 5 squared, 4 squared, 3 squared, etc. So how to put this in a fraction, in something we understand more clearly? Now we can take out the z to the power minus 1 definitely out of this complete series, so everything goes here and goes up by 1. So we have z to the power minus 1, z to the power minus 2, etc. You see actually all here. And then what? Now we can still do something. So we can recognize here something that can be helpful later. That's actually shown here. So we can see that the z to the power minus 1 can stay here. And we can have this 1 minus z to the power minus 1. And then this part also times that one. You can recognize that maybe not easily, but then you need to do here the long division, and then you can create this. So what do we do now? Now we have this, and this thing here is again put in a fraction by using the calculus theorem for infinite series. So this is the infinite series can be expressed in closed form. Now we have here some infinite series. So 1 over 1 minus z to the power minus 1 is this one. Now if you square that, you have this one. If you make that to the power 3, so cube that, you have this one. In this case, we can use these theorems or expressions in order to get that one. So which one do we use? Now, this one is similar to that one. You might say why? Now let's look at it. K plus 1 times k plus 2 over 2. So I go one by one. So k is 0, that means 1 times 2 over 2. And then 0 to the power 0, so that means 1. That's the first term. And then I make this 1. So 1 plus 1, 2 times 3, 6 over 2 will be 3. And then 0 to the power minus 1, and that's this 1. So if I do it for k is 2, so k is 2, it will be then 2 times plus 1, 3 times 4. So it will be then 12 over 2 will be 6, and then times 0 to the power minus 2. That's all shown here. And that will end up to this one, because that's shown here. So this is what we can use as a formula. Thus we have this whole thing here can be also expressed like so. And now we have this term, so we can put it here in the numerator. And again, if you don't like the negative exponents, we can multiply the numerator and denominator by, in this case, z to the power 3, in order to make this z minus 1. So this will be then z, so z squared comes here, and then z comes in this expression. Now this is now the z-transform of this function. Okay, let's see also that in the MATLAB, because this is now the definition of our symbolic variable, in this case k. We have here the x is equal to k squared, and this is now the z-transform of that, and this is the result. Would you see z times z plus 1 over z minus 1 quantity cubed, or to the power 3. So we can say this is indeed as we have expected. Alright, this was our video about the z-transform using the important elementary functions and properties, and we have also worked out several examples and verified this in MATLAB. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.